All right, so let's get started. Today we are actually I will actually introduce the kind of core idea of what we do with calculus and why it's useful, which is the derivative and rules for derivatives. Close the door after you come in, please. Okay, so in our previous classes, we have been talking about a bunch of stuff to get ready for doing derivatives. So mainly looking at these nonlinear functions and visually recognizing certain things about them. Today, I will talk a little bit about the idea of a limit, which is connected to the preview homework that I gave you. And then today we'll actually see kind of the definition of a derivative. Main focus here. Just so you know, this is a temporary tentative date, but probably that is when our exam will be. So this is week 12, so you know. We have 3 weeks left of sort of material. Week 15 is the start of the official exam week. I plan to do just review in that week, and then we missed a lot of classes just in general this term. So week 16 is all makeup classes, and this is the first day of that makeup week that I plan to use for our exam. So I'll post on our classroom page kind of a more official thing announcing that, but probably that's when the exam will be. Also, since lots of us are here in person, then we'll have that option for the final exam if you want to just come and do the exam here in the classroom. You don't have to do all that scanning and selfies and all that. If you're online, it's still fine to do it online if you're not in Korea, whatever. But if you want to come do it in the classroom, you'll have that option. More details about that later as well. So that's where we're going. When I said this in the other 2 classes, people asked, so I'll just say it here directly. Yes, the final exam is about the whole course, not only the second half. I said that right after the midterm. The final exam will be 25% pre-midterm material and 75% post-midterm material. A real final exam should be about the whole course. Okay, so it will be about the whole course. All right. Okay, so from last time, let's just do a bit of review with this function here. Let's identify all of the parts that we have. So in each of these, I'm interested in the x coordinate, the x value of each of these things. So what is the x value of the y-intercept? 0 here. Okay, so there's our y-intercept. Draw our line down. It's 0 on the x-axis. What about the zeros here? -4, -2, and 3. So that's 3 zeros there, we see. All right, minimums, maximums, what do you see? All right, so around -3, a minimum. And +3 and 0 here. All right, so 3 minimums, or sorry, 3 turning points, 2 minimums, 1 maximum. Let's do this classification also. This first one, global. And we know that because if we sort of imagine a horizontal line going across, it is the overall lowest point on that function. So that is a global, I'll just write G there. That is a global minimum. The next one here, the maximum point, what type is that? Okay, so local, obviously over here, this part is higher. On the left, it's higher as well. So only a maximum in a local sense. And then the last minimum point, okay, so also local. We have other points that are lower on function. All right. So let's get rid of all these and redraw the turning point. 1, 2, 3. So based on the turning points, how many intervals of increase or decrease do we have? Okay, so 2 and 2, 4 total. So we're going, so first it's the interval of decrease. I know the arrow's going up here, but we always read kind of left to right. These are all negative slopes. And then we hit a turning point and now the graph is going up. All positive slopes and then negative again and then positive again. So decreasing, increasing, decreasing, increasing like that. All right, last thing, we'll talk about the sign. So this function would be some f of x equals ax, some exponent plus dot, 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 dot. So the leading term here. So our coefficient a, is this going to be positive or negative? Based on what? All right, so right side is going up like this. So it's positive. That's the only way that could end up going up like that. Coefficient is positive. What do we know about the exponent on this? Okay, even number because the two sides go in the same direction here. So the left and the right going in the same direction. If it's either both up or both down, that means that it must be an even number. So 2 or 4 or 6 or 8. Can you tell me a little bit more? If you had to take a guess at the exponent, what would you say? Why 4? 4 intervals. Good. What else tells us? Okay, what about the turning point? Okay. Okay, so that as well, turning points. So turning points plus 1 must be the minimum number of the exponent. What about the zeros? At least 4. Okay, so a little bit more about the the zeros. So we see 1, 2, 3. But if we look here, we could imagine the graph just going a little bit lower like that, right? And then that would produce 4. We see 4 would clearly be possible here. So the zeros are a minimum number for the exponent. So if there are 3 zeros, the exponent must be at least 3, possibly higher, but we also know it's even. So basically it's telling us it can't be 2. With the number of zeros we have, it can't be 2, must be even and something 3 or larger, but 3 is not possible because it's even, so must be at least 4. So intervals, turning points, zeros all give us clues for the minimum size of that exponent. It could be more, it could be 6 or 8 or 10. We could make that graph, but minimum is 4 here. Okay, that's all the parts. So just kind of visually recognizing this stuff. Anyone have remaining questions about this? All right, so let's talk about this thing from the preview homework. So I asked you to find what this function is equal to when x is equal to exactly 7 and then very, very close to 7. So let's try to do some simplifying first here. Can we reduce this and just make this a little easier to look at? All right, so x minus 7, x plus 1 on the top here, and then x minus 7 on the bottom. And then if we reduce this, this turns into x plus 1. Except, or a little sort of condition here, x must not be equal to 7, because we had this dividing by 0 problem here on the bottom if x is equal to 7. So x plus 1 tells us values for every point here except when x is equal to 7. That's the one point that we can't use this for. So that's here on our graph. We have this big question mark. What happens there? So I'll excuse me. I'll briefly explain the idea of limits in a moment, but just before that, I think not everyone is necessarily familiar with this kind of function notation like this. Like this is the same as just writing like y equals whatever, but this notation is useful because we can do things like this. Before, we would say, well, what is the function when x is equal to 3? And we would write something like this, x equals 3, and then sub that into the equation. So y equals 3 squared, like, and all of it. That's a little bit extra writing that isn't necessary. So instead of that, we can just write this. So what is the y value when the x value is 3? That's just telling us directly what number we want to put in. And what is that in this case? 4. So the function is just x plus 1, which would just be 3 plus 1, 4. So we can use this for other numbers as well. When x is 4, what is the function? 5 and 6, 7. Okay, so those ones are the easy ones. Again, x equals 7 is the harder case. So this is just how this function notation works. We're going to use this a whole lot as well. Okay, so this is what we have, and we want to figure out specifically when x is equal to 7. All right, well, what we can do, a little bit more first. You can kind of see what's happening here, right? We can imagine, well, if we go really, really close to x being equal to 7, what number does it look like we're getting close to? 8. So that's just intuitive. That's pretty easy to see here. If x is really close to 7, then this thing gets really close to 8. We have a fancy math way of writing this, which is what this idea of limits are. So we would write it like this. We have some function, and then we write this limit thing in front. So limits as x approaches 7 of whatever that function is. So in this case, our function is this. So we want the limit as x approaches 7 of x plus 1. So this is just the same thing that we were saying. Make x very, very close to 7 and then see what happens. So a little more formality here. We kind of have two directions. Our x value could be close to 7 but slightly below, or close but slightly above. So we would write that in this way. So the limit, really, it has two parts. We have the limit when we're slightly below the thing, and we write it like this. Limit as x approaches 7, and then a little minus sign after the 7 there. That means just slightly below 7. And on the other side, a little plus after the 7. That means slightly above 7. So approaching from just below and approaching above. So the values we would put in here, 6.9, 6.99, 6.999, like that. And here, same idea, but 7.1, 7.01, 7.001, 1. Then we just get closer and closer, and our results from below 7, we'll get 7.9999 to infinity. And on the other side, we get this 8.0000 to infinity, and then a 1. So if you remember when we talked about infinite sums for the geometric series a few weeks ago, and I asked you that question, if I want to walk to the wall, but I do it by just walking half of the distance each time, half of the distance, half of the remaining distance, then do I touch the wall? And most of you guys said no. So in a physics world, in a real world, yes, that's true. But in the math world, we actually go to that point of infinity. And at the end, we do actually touch that wall. So we can kind of use the same idea here. We go to infinity and infinitely close. So from both sides, if we are getting infinitely close to the value of 8, then it's just 8. So I know in this example, it looks kind of silly. Like we knew it was 8. We just kind of put it in that. We could have done that right away. I chose this example just to make kind of the two parts clear. But limits, this math tool, lets us get around certain calculation problems like this dividing by 0. So here's this formal math way of kind of showing, well, if I'm slightly below, we get infinitely close to this point. And if we're slightly above, we get infinitely close to the same point. From the negative side and the positive side, we get really, really close to 8. So that must be the answer. That must be the result. So that's this idea of limits. There's certainly a whole lot more that could be said about these, but this is as far as we are going to go. And we'll use this. This is the last little tool that we need to understand the definition of a derivative. So let's get to that. This thing. This is a very important kind of definition or formula thing, and I'll explain this and see where we're going with all of this. Just to remind you, our whole goal with this is, let's say we have a curve like this blue line. I choose just some random point on this curve, and I want to know what is the slope of the curve at that point. And we do that, we figure that out by just drawing a straight line that touches at just that one point, and then just finding the slope of that line. So let's see how we can accomplish that. Forgot I had the slide. Just to remind you, we're doing all of this for our total revenue curves. This will help us find the exact top point. And for these total cost curves, it will help us find this minimum average cost, minimum marginal cost here. We'll get back to that in a little bit. All right, so just to get you starting to think about this, if I give you 2 points, let's say here and here, 2 points, can you tell me the slope between these 2 points? Yes. So this is not a difficult question. We can draw a line between the two of them, and our slope, what is our slope formula? Right, delta y over delta x. And we have, there's our x1, y1, and this one is x2, y2, and then this turns into y2 minus y1 over x2, 1. So again, just the delta x, the delta y just means change in x. Like what's the difference? What's the gap, the change in x between these two values? And same for y. So if I give you 2 points, you can tell me the slope. That's a pretty easy question. How about if I give you 1 point? No. kind of, and that's what we're getting to. If we just have a situation like this, though, it's impossible because, well, which slope? I can draw a million lines through that point. Which slope do you want? There's no clear definition of that. So slope from one point is kind of a weird question to ask, but we'll see how it makes sense in the particular context of a curved equation. Okay, so we'll start explaining this with the function y equals x squared. So it looks like this. We're going to zoom in on this little corner here, and the colors don't match changing color. So now it's orange. That's my mistake. I have to fix these slides later. So this is our y equals x squared. It looks like this. We're just zooming in on this little part of it here. So here's the points that we've chosen here. And I want the slope of the curve at that point. So I've made this tangent line, this blue line here, and we want the slope of that tangent line. But how do we find the slope of that line? Like mathematically, precisely, how can we find it? Okay, so kind of, we have the formula, but we have some problems with this. So we don't really have 2 points on this. We just have 1 point on this line. We want a slope, but we only have 1 point. So what we're going to do, so this point, we're just going to call the x value here a, which is whatever. So then the y value is just the function at a. It's just a squared in this case. So a and f of a. So slope, we'll use this slope formula, delta y over delta x, but we need a second point. So what we're going to do is we'll say we'll kind of draw a second point on our function here, just way up here, and we'll connect it. So we have this new red line here. And again, our goal is the blue line. We want the slope of the blue line, but we are going to estimate it with this red line. Right now, this red line is a pretty terrible estimate. It's very different, but we'll start there and we'll make it better. So we're going to define, well, what are the coordinates of this new point here? Well, if this point is A, and then we have our delta x here is h, then it must just be A plus that difference. A plus h is the x coordinate there. And then the y coordinate is just the function at a plus h. So a plus h squared will give us the other value there. So it looks like we have 2 points, and then we can just use that with this slope formula. So all this is y2, this is y1, and this is x2, and this is x1. So that's all we're using. Okay. So currently, this red line is a terrible estimate. It's really, really different from the blue line. So what we can do is just take that h and just make it a little smaller. And we just slowly move it in and closer. So it's getting better. The red line is becoming a better estimate. And we just want that h value to get close to 0. So the smaller it gets, the better our estimate is. But what would happen if the h value becomes 0? Slope would not be 0, but look at the formula and look at what would happen here. Yeah, so like we have a minus a, so those obviously just cancel out, those are gone. The bottom is just h, so if h is 0, we're dividing by 0, math problem, we can't do it. So We're going to use limits again to just get around that little inconvenience. And then we can maybe get to this point where h actually becomes 0, but we don't have this math problem. And then our red line will be a perfect estimate for that blue line there. So we're just going to do these two slope formulas, and we're just going to add this little limit thing in front. So limit as h approaches 0. We can't do it exactly directly when h is equal to 0, but we'll just do this limit thing. Okay, so let's do that. Now it's time for the algebra part. So this is our definition, same thing that I had on the previous slide up here. And the function we're working with is x squared. And this is a different a value than we had a moment ago, but the math will be a little easier here. So this is our a value. What is the slope of this function when x is equal to 2? So we're going to use this big, long definition thing and then figure out exactly that. Oh, here, limit 0 of f. Okay. Okay. So that's our whole thing here. And let's just substitute in all the parts. So let's do the bottom of the fraction first. That'll be a little easier to think about. A plus h, our a value we said is 2. So the bottom is just h and then minus a, so minus 2. And then the top here. So f of a in this case, what is that? 4. So f of a, and the function just means squared. So that's just our a value squared. So then f at 2 is just 2 squared, which is 4. Okay, so on the top we have minus 4. And the other part here. So we have f at a plus h, or really we have f at 2 plus h, which is 2 plus h squared. And what is that if we expand that? Four plus 4h plus h squared. Okay. So those are the 4 parts. If we take that 2 plus h and we expand it. So we have 4 plus 4h plus h squared minus 4. So that's the top of our fraction. Okay, and let's simplify. So limit h approaches 0. What's the first thing you would see to simplify on the top here? Right, so the 4 and the 4. We're going to do this in lots of separate steps so we can all see exactly what's happening. And then the later examples will go a bit faster. On the bottom, 2 and 2, those are just gone. We just have h. Okay, what is the next thing you could notice? All right, common factor of h on the top. Yes, I'm going to do that in 2 steps, just so we can all see. So common factor of h on the top, 4 plus h, and then over h. So h on the top, h on the bottom. Continue here. So limit is h equals to 0 of 4 plus h. And now what can we do? How do we get there? That's what we want, but how can we do that and like make it mathematically valid? How can we, what's the next step? How can we simplify this?
4 plus 0, so it's 4 because h is approaching 0, right?
Okay, so we'll evaluate the limit. What we do with the limits, so here we have this limit thing in front. Our goal here is to get rid of that. We don't want that limit. We want to actually be at the point where h is equal to 0. But here, if we do that, we are dividing by h, dividing by 0, math problem, so we can't do it. So we just don't touch the limit. And our next step, we want h to be equal to 0, but dividing by h, can't touch this, just got to leave it for later. Here, still dividing by h, still dividing by h. But then here, no more dividing by h. So that problem is gone. That math problem, we made it disappear by canceling out our h terms. So we evaluate the limits just by doing this. We set h to be equal to this thing. Just substitute in that value. So 4 plus, and then 0 for h, and then that's 4. So this is how we evaluate the limit. If there's no math problem stopping us from doing it, then we just do it and we get rid of the limit part. So this whole thing is telling us that for this function, x squared, when x is equal to 2, the slope is exactly 4. It's not close, it's not a guess. We have this, we kind of went to this point infinity using these limits, and we know exactly that the slope is 4. So we resolved the problem here. We're going to do this again for this one, where x is equal to 5. I've kind of run out of space to write here. I'll start it, and then I'll have to erase stuff. Well, maybe we can just do this with fewer steps. So our first thing, let's say this step here, let's recreate that step, but for x equal to 5 here. So limit is equal to 0. So this step, when x is equal to 5. 20, I'm going to leave, I'll leave it back. 25 plus 10h, h squared, minus 25. And on the bottom, I'll leave out the 2 and the 2, or the 5 and the 5. Let's just write h. So every time the bottom will just cancel out to only h. Okay, so this is when x is equal to 5. We just did 5 plus h squared, and we expanded it like this. I looked at some examples of this in the workshop on Thursday last week. So if you want to see some more of that, you can look at that video, or I'll show you another thing in a moment, which will help simplify those. Okay, so here, if we're going to simplify, same thing, just the 25 and the 25, right? Obviously, you can probably guess where this is going. So 10h plus h squared over h. Factor out, take the common factor of h out of the top and eliminate with the h on the bottom. I'll combine those two steps. Limit is equal to 0 of 10 plus h. And then we substitute in our value of 0 for h. So 10 plus 0. 10. That's it. All right, we did not run out of this. So when x is equal to 5, our slope is exactly 10. Do you notice a pattern between or with these here. The x value and then what the slope was. Okay, so it's double the value. We've only done 2 examples of this so far, so it looks like we have that pattern, but let's try to prove that that is actually what's happening here. So I'm going to erase all of this. Okay. So let's do this, but where I've changed things a little bit here. Instead of a, we just have x. Let's use a general x value, not some specific a value, but just generally. So that will tell us the slope for any x value that we put in, not just these particular numbers that we've been using. All right, so we're gonna write out the whole thing again. Limit h approaches 0. Minus x over, and I'm just gonna write h on the bottom. Save us time. Okay, so h on the bottom, f of x here is going to be what? X squared, because f of x is x squared. That's it. So that one's easy. F of x plus h, what will that be? X squared plus 2xh plus h squared. So that's our expansion here. Just remember, right, one more line. This is clear. This would be x plus h squared, which is x plus h. Expanding. Okay. All right. So let's take those things and put them into what we have here. Limit 0 of x squared plus 2xh plus h squared minus x squared. All of that over h. And we'll take this as well and just try to simplify. The way that we simplify is going to be very similar to what we did for the previous example. What's the first thing? Okay, so the 2x squareds will cancel each other out. So 2xh plus h squared over h. And okay, so common factor of h on the top and with the h on the bottom, those here, limit 0 of 2x plus h, 2x plus h, and now we can just do the limit. We have no more dividing by 0 problem. So 2x plus 0. 2x. Okay, so it turns out we were right. So this for any point x, the slope is just double that value, 2x. So this is our mathematical proof that yes, that pattern is actually what we have here. So this is the algebra version. I'll show you it as a graph in a moment. Everyone's done right. Okay, so that thing that we made, that 2x, that is called a derivative. This here. So our x squared, f of x equals x squared is our original function. And the derivative of that is 2x. And we write it like this. F prime, the original is just f. So this one, we add this little tick mark and we read it as f prime. So f prime of x is 2x. So this thing is the derivative. So the derivative itself is also a function. Just like imagine y equals 2x. That's a line. That's a thing that we can put on a graph. We can visualize that. And that's exactly what this blue line is here. So the derivative is itself also a function, can be graphed. And what the derivative does is it tells us the slope of the original function for any point on that function. Let's choose a few examples. Let's say here. My original function, the orange one, when x is equal to 1, what is the slope? What is the slope of the orange function when x is equal to 1?
2.
2. Because 1 times 2 is 2. Also, look at the graph. The blue one, the y value of the blue one tells us the slope of the orange one. So that's the visual thing we can recognize here. The y value of the blue one there, when x is equal to 1, is 2. So that is the slope there. Let's choose another point here. On our orange graph here, x squared, when x is equal to -1, what is the slope?
-2.
-2, because -1 times 2 is -2 also. We just line it up vertically, find out where the derivative lines up with that same x value. What's the y value there? It's -2. So that's the result, it's -2. Let's try another one. Here, when the x value is -2, what is the slope? -4, because again, 2 times -2 is -4. Also, okay, that part's not so hard. The graph visually, this is what I want you to get used to. What's the slope at that point? Just line it up vertically. Draw that straight vertical line in your brain. And what's the y value for the derivative at that point? It's -4. That's the slope. It's -4. Okay. So again, the y values of the blue thing are telling us the slopes of the orange thing at the matching x values. If you don't fully understand that right now, then after class, just spend like 10 minutes or an hour or whatever, just staring at this graph until that makes sense to you. We're going to look at more complicated ones later. If this doesn't make sense to you, the other ones won't. So make sure you understand that. Y values of the blue one are the slopes of the orange one. One other little just kind of point here. Some people get confused by this. We do see that the derivative and the original function intersect. We don't care. Intersection points don't mean anything. We don't interpret them. There's no math meaning. It doesn't matter. The original and the derivative often have no intercepts at all. We don't calculate them. We don't think about them. It doesn't matter. The only thing is find the x value of 1, line it up vertically with the same x value on the other one. That's the relationship we care about. Okay. Questions about this? Does it kind of make sense? Okay. How many people have done derivatives before? I've seen some. Okay, a few people. Okay, people who have not seen this before, does it make sense? A little. Okay. All right. So if you haven't seen this before, again, stare at this graph after class until it makes sense to you. This is the easiest possible version of it. Okay. I have one more long version of this that we are going to do with this function here. So what we did for the previous examples, we had to have that whole definition of the derivative, and we did that big long thing just to find the derivative for one function. We don't want to do that every time. We want to have shortcuts and more clever ways of doing that. So we'll do it a long way one more time, and then we'll notice a pattern, and then we'll just use our shortcut rules after this. But we're going to do this long way again with this function, 4x cubed. 4x cubed. All right. So limits h approaches 0 of this whole thing here. So our h on the bottom is always there. So that's simple. That's easy to think about. For the other one, so minus f of x minus our f of x here is 4x cubed, so minus 4x cubed. And then we have our other part. So f of x plus h would be 4 times plus h cubed. So that's our x, that's our y2, that's our y1, and that's our delta x on the bottom. All right, so let's figure out what these parts are. Most of this isn't too hard, but this thing is a little annoying. So let's think about this. That is what I'm going to show everyone. So x plus h cubed. Can anyone tell me right now what this is? Nope. Nope. You're thinking if it's x minus h here, but this is x plus h. We're going to have 4 different parts. Okay, wait, slow down one more time. Okay, x cubed. Yes, but tell me in a more straightforward order. X squared. Uh-huh.
Plus x squared plus h cubed.
All right, there we go. Okay. So there's a rule, there's a pattern we can notice to jump directly to this. So just for clarity, x squared plus 2 x h plus h, and then plus h again. So we did this before. So expand. Okay. So we did this. We did this for the x plus h squared, and then we're just multiplying by x plus h again. And we could do that manually, and we would get this whole thing here. But there is a faster way of doing this with called binomial theorem or Pascal's triangle, which looks like this. Tell me the next line. Okay. And what is the pattern here? How do we create each new? Okay, so this 2 value is 1 plus 1 gives us 2. This 4 value is 1 plus 3. This 6 is 3 plus 3. This 10 is 4 plus 6. You just take the 2 values that are above it and add them together, and you get the next thing. So the next row would be 1, and then 1 plus 5, 6, 15, 20, 15, 6, 1. So look at the numbers that we have here, specifically this row and this row, 1, 2, 1 and 1, 3, 3, 1. And then look back here. The coefficients, 1, 2, 1, and coefficients here, 1, 3, 3, 1. That's not an accident. That's not a coincidence. It's from this exactly. And we could have a formal proof showing this. So these are telling us the coefficient of a thing like a plus b squared. And this thing is a plus b cubed. And the next one would be a plus b to the exponent 4, et cetera, et cetera. Okay, so if you have a thing like this, a plus b to some exponent, you can very quickly see what that thing would be. And you don't have to just manually add all the things together. That would take forever. Okay, so just a fun little side thing there. Now we can get back to what we have here. So limit 0. And we did that expansion. That's here. And we have 4. I'm going to, I'll kind of leave the 4 separate, as you'll see. It will make sense in a moment. So 4x cubed plus 4 times 3x squared h plus 4 times 3x h squared plus 4h cubed minus 4x cubed. And all of that divided by h. Okay, so we have this big long thing in the top here. What would you notice first if we're going to eliminate? Okay, so 4x cubed minus 4x cubed. So those disappear. That's gone. And that's. So limit h approaches 0. 4 times 3x squared h plus 4 times 3x h squared plus 4h cubed all over h. What's next? Okay. Okay, but we don't have a 4h on the bottom. We just have an h on the bottom. So I'm going to leave the 4s in there separately, and we'll see why I'm doing that in a bit. So limit. We'll take out the common factor of h. I'm not going to write it in 2 steps. I'll just do it in 1. So what is our new next line here? Okay, so 4. I'm going to write it as 4 times 3 x squared okay 4 squared. So the h's on the bottom is gone, and then each of these terms has lost 1 h from them. So this one has no more h, this one has 1 h, this one has 2 h's here. Well, we're getting to that. I'm showing you how we get the formula. Okay, I need a little more here. Okay, what is the next thing that we could do? Okay, so we have no more division by h, so we don't have that math problem there. We can set h equal to 0. So that will give us 4 times 3x squared plus 4 times 3x times 0 plus 4 times 0 squared. Okay, so let's notice what's happening here. When we think back to this first sort of expanded step here, we had 1, 2, 3, 4, 5 terms on the top. 2 of them canceled out right away. Here, when we set our h value to 0, that thing's gone and that thing's gone. So that was the 4h cubed, and the other one was this one, the 4 times 3x h squared. So look at what's left. Only the second term stayed. Everything else got canceled out and eliminated. So just that second term stayed. So that's our answer here. 4 times 3x squared. Yeah, so okay, now we'll actually finally do this. 12x squared. I'm writing it as the 4.3, sorry, 4 times 3 because I want to show, yeah, so that's the question now. What is that pattern?
The exponent.
Okay, so you guys have learned this before. Anyone else who is seeing this for the first time today, can you notice a pattern between this thing and this thing? Anyone who's seeing this for the first time? Have you learned this before? I don't know if I, okay, tell me what you think. Okay, but this thing is the slope. The thing that we found is the slope, but we want to know how we got to that point. Okay, so the pattern here is we take our exponent, it's 3, right? So 3 times the coefficient, that's our 4 times 3 here. So multiply the coefficient by the value of the exponent, and then you just subtract 1 from the exponent. That's it. And as I showed you, in this expansion, everything else cancels out. So the only thing that will ever be left is the second term. Even if we have a much larger exponent, like x to the exponent 10, only the second term will remain. So that's our shortcut here. If we notice that pattern, then we can jump straight to this rule. I'm going to erase this. Does everyone? I'll give you a minute to write, and then, or a second to write, and then I'll show you. All right, we're ready. So after all of that, here is this little shortcut rule. If our function is just any y, so any a and x to any exponent n, then the derivative, which again, the derivative is a new function that tells you the slopes of the original function for any point, then it's a times not to the exponent n, just multiplied by the value of that exponent. So a times n, and x, we just subtract 1 from the exponent. So we just spent 1 hour making this. Okay, so this is our shortcut rule here, but we went over all that derivation because you kind of need to see that to understand what calculus is doing. If I just showed you this, it wouldn't make any sense. Okay. Wait, you guys never saw this?
No, never.
Did you ever understand what you were doing, or was it just a little? Okay. All right. Okay. Okay. So, all right, different styles of teaching, but I think if you actually understand it, you can remember it better and you can use it better. So, okay, so that's why we did all this. So this is the shortcut method. This is probably the most important derivative rule. We are going to look at two more, which won't be very hard really, but this is the main one. And then we'll do a bunch of practice with these, but this is as far as the other classes got. So this rule here is the whole point of today. So please look at that and remember that. And let's go back. So this thing here, actually, let's go back a few more. So this is the first idea. The derivatives, the whole idea of calculus is just coming from this basic slope formula. So y2, y1, x2, x1. So that's it. That plus a limit made this field of calculus, which is now widely used in like every field of engineering and science everywhere. So this slide is telling us the goal and how we get there. And then this one is the most basic version of a relationship between an original function and a derivative. We are going to get more complex than this. We will look at second derivatives. We will look at more complex curves. So we'll have a graph like this that's harder to understand. So again, please make sure you look at this graph and you understand the relationships between the two functions here, because it's going to get harder and you won't understand those if you don't understand this one. Okay. All right. Questions? Anyone? Yeah. We did. And these ones I did that. We can. Again, I'm trying to help you guys remember it and understand where it's coming from. But when we see it like this, it's easier to remember that's x2 minus x1. So I'm just writing that to help people see the connection. Yeah, so if your teachers taught you this without actually explaining it, then they would just put H on the bottom. Yeah. Okay. Also, we kind of don't really need to write it because, as I mentioned, H is the difference between the two X things. So H is delta X. It's just a different label for delta X. It's the exact same thing. So you're right, we could just put delta X on the bottom or H on the bottom, but I'm just putting it here for a bit of clarity. Other questions? All right. So we're going to talk more about notation stuff. There's derivatives and all this calculus definitely gets more complicated. There's some more rules. There are some really hard rules, but we're not going to do those. The power rule is the hardest one that we're going to do. So once again, derivative is the thing that tells us the slope of whatever original function we have connected it to. And then using that derivative, we'll find all these important points. Here's where the slope is flat and the maximums and minimums and lowest possible slopes and all of that. So the derivative is also a function. It's not a number, it's a function. It also can be graphed and visualized. And we'll see all kinds of applications. I forgot to write them here, but there are some practice questions and some textbook sections that will actually explain this in more detail than what I have here. So if you want to look at that, that's all there as well, and that's on our class page. All right, I think we're done just really early again. Yeah. Okay. Congratulations, everyone. You guys are quick. All right. I'll see you on Thursday and more calculus. Fun times. Yes, attendance papers are here and you guys can sign. All right. Goodbye, everyone. See you Thursday.